By the turn of this century, the beam walker may be exploring Mars. Slow, but very, very sure, it would carry cameras and instruments for humans back on Earth. But engineers and scientists want to put human footprints there too. Their real goal is actually colonizing Mars and maybe changing it for good.
Unmanned rovers, like Beam Walker, are essential in providing us with the next step in exploration capability. But it is not at all out of line to think that within the 21st century, we can reclaim Mars for life. I think this is the most important thing that human beings in our time could be doing.
What we're going to see here is one of the most spectacular features of the solar system, the Grand Canyon of Mars.
One of those who knows most about the Martian surface is Dr. Mike Carr. For 20 years, he's been analyzing data for the US Geological Survey.
We're circling over the eastern edge of the canyon now, and we're going to go westward up the Tharsis Ridge. We're passing now over the center, the widest part of the canyon, that's 7 kilometers deep, and the thick sequences of sediments in there. We just passed over the labyrinth at the eastern end of the canyon and are going toward a line of volcanoes. Now passing over these huge volcanoes, 3 times as high as those in Hawaii and much wider. Now we're turning eastward again, back toward the canyon, over a volcanic plain. Coming up on the edge of the canyon, and we can look down into the canyon, see a huge hill in the middle of the canyon that's formed of water-lane sediments. Now again we're coming into the main part of the canyon, see the facing wall several kilometers high. And now sweeping over the volcanic plains to the south of the canyon. We're coming back now deep into the canyon, and there's a vertical exaggeration here, which is giving a false impression of the relief. And now we can see one of these huge Tharsis volcanoes on the horizon. Just passed over it. This is a huge bulge on the surface of Mars, and these volcanoes lie on the center of that bulge and are indicative of an enormous amount of volcanism that's taken place. It's almost as though magma was pushing up this bulge from below and causing these formation of these volcanoes. Now we're back at the canyon and looking down into it. Well, Mars is the most Earth-like of the planets, but there's no way you'd want to live there, or it would be very uncomfortable. The temperatures are extremely cold. They're as cold as the coldest places on Earth, as cold as Siberia and Antarctica, minus 60 degrees centigrade. And then the temperatures go on down from there, down to minus 100, minus 150 degrees centigrade. Also, the atmosphere is extremely thin. It's less than 1/100th of the Earth's atmosphere. And you can't breathe it. It's almost all carbon dioxide. There's just traces of nitrogen and argon. And it's dusty. If you kick the ground, you kick up a cloud of dust. The wind blows. Generally, the winds are pretty light, but they can gust up to 100 miles an hour. In fact, they blow up this dust and cause enormous dust storms. So it's a dusty, windy, cold, and dry. It's not a very pleasant place to have a vacation.
Flash Gordon calling emergency.
Though we now know the planet is very hostile, it's long been a setting for human fantasies.
Good landing, Flash. We're right near the tunnel entrance. I hope Captain Sutton has been able to leave it unguarded.
Flash, please let me go with you.
No, Dale, you stay here and help Ronald guard the prisoner.
People have always projected their own ideas of the world onto Mars, and the less we knew about Mars, the easier it was to project individual visions onto it.
Stanley Robinson has written a science fiction trilogy based on the idea of terraforming Mars, making it livable for human beings. Scientists have never been short of speculative ideas about the red planet.
With the invention of the telescope, astronomers, Schiaparelli the Italian and then Lowell the American, They, in their scholarly works about what was going on Mars and what they could see through their telescopes, they saw what they said were canals, and Lowell himself postulated that perhaps these had been built by an intelligent civilization that needed water to supply a drying world. It was a fabulous story. H.G. Wells said, well, what if this civilization was malignant towards us? In Germany, Kurt Clausewitz wrote a book called Two Planets around the turn of the century, and in which he said, well, this civilization must be technically very competent. I mean, it's a very German view of things, and he was interested in the civilization for that reason, and this had an enormous impact on the German rocket scientists of that generation, including von Braun.
The Soviets, too, were obsessed by space travel. They pictured Mars in expressionist style in Elita, made in 1924. The Bolsheviks travel there and bring about a second revolution in the image of 1917. Once again, people impose their ideal vision on Mars. But now, our ideas take a different form.
Now we really know the world that is there. And it's no longer as blank a slate as it was before. And so this has brought us to the moment where you can imagine terraforming Mars.
Engineering? Engineering is go. Mission director? Mission director is go. And liftoff of the Titan III rocket with the Mars Observer and America's return to the Red Planet.
I believe that before Apollo celebrates the 50th anniversary of its landing on the moon, the American flag should be planted on Mars.
Once again, the planet is being used to support a national political vision. With the space program stalled and the Soviet Union no longer a technological rival, the Red Planet has been invoked to replace the Red Menace.
It will revolutionize everything from computers to communications, from medicine to metals, regaining and retaining America's high-tech competitive edge. It will create new technologies, new industries, and new jobs.
Mars Observer should orbit the planet later this year. Both America and Russia have announced programs to send first robots like the Beam Walker and then humans by early in the next century.
Touchdown, we have touchdown.
The first and so far last robot to land there was the Viking mission in '76.
Well, there are rocks, yes. There's rocks and there's sediment, but it's just incredible to see that the Mars, is really there.
But hopes of finding life were dashed. The planet seemed quite barren. That very absence of life caught the imagination of a young research scientist.
I got interested in Mars in 1976. I was entering graduate school, and that summer, Viking had landed on Mars, and by that fall, we were getting data back. And so here I was, my first year of graduate school, and Viking sending back information from Mars, and basically the information was saying that everything you need for life is here, but there's no life on this planet. Sort of a lights on, nobody home message. And I got intrigued in that and by that, and I thought, well, let's try to understand that. And in particular, what would you have to do to introduce life there, to make it habitable? I thought it might be a summer or semester project. And here, 15 years later, I'm still investigating that problem, that question. It's obsessed my scientific career, if you will, and it's led me into many fascinating directions.
And many sciences would be needed for McKay's scheme to transform Mars. Physics and chemistry to heat the planet, change the atmosphere and liberate frozen water, then biology to seed the surface and start the processes that would turn it into a semblance of Earth, where humans could breathe under open skies, not in spacesuits. But spacesuits are how it would have to begin.
The spaceship for a Mars mission is a huge structure.
The journey to Mars lasts a year. Just going there stretches engineering to its limits. The initial NASA plan involved sending a crew with 100 tons of fuel to bring them back. That increased the takeoff weight by 400 tons. The huge ship couldn't possibly be launched from Earth. But now, even NASA engineers doubt that they could build and assemble such a ship in space. Robert Zubrin is a designer at the company that built the original Viking lander. His idea is to use Mars, not fight it, and NASA are now thinking along the same lines. More than a technique for getting there, this is a new way to think about working on Mars.
We said, look, let's figure out how to do this in a smarter way. Let's figure out how to use what's there. Why ship to Mars rocket fuel when Mars's atmosphere is made out of rocket fuel?
Zubrin's plan is called Mars Direct. It would start with the launch of an unmanned mission. A rocket, about the size of the one that took men to the moon, would go direct to Mars. There'd be no painstaking assembly in orbit. The idea is for the return stage to land automatically and then get to work exploiting local resources.
Now, in some of the tanks that are later going to contain methane and oxygen fuel, we have about 6 tons of liquid hydrogen. And we run a pump and we acquire the Martian air. And Mars's atmosphere is 95% carbon dioxide gas. Now, we know that for a fact because we had the 2 Viking landers on the surface of Mars operating for 4 and 6 years respectively, and that's what Mars's atmosphere is every day of the week. Now, you run the pump, you suck in the CO2, and you can react carbon dioxide with hydrogen to make methane and water. The reaction could be, is written like this. You take hydrogen from Earth, and you can react that with CO2, which is carbon dioxide, and the product is methane, CH4, that's natural gas like you use in a stove, and water, H2O. Okay, now the methane that comes off, that's your rocket fuel. But you can't just power a rocket with fuel, you also need an oxidizer to burn the fuel with. So what you do is you take the water, the H2O, and you electrolyze it into hydrogen and oxygen. Okay? The oxygen that comes off you store in a tank, and that's your oxidizer to burn the fuel with. And the hydrogen you recycle back to react with more Martian CO2 to make more methane and more water and so forth. Now this is very old-fashioned chemistry we're talking about here. This is gaslight era technology. This is something that could have been done in the time of Jules Verne.
The humans would arrive only after the return stage signaled that the tanks were full and all was well. They'd bring no fuel, for it would already be there, made on Mars.
What we've accomplished by taking this approach to living off the land is we took 6 tons of hydrogen with us from Earth and turned it into 108 tons of methane oxygen on the surface of Mars. It's a leverage of 18 to 1. It's like an explorer on Earth getting a caribou by carrying with him the weight of a bullet instead of the weight of the caribou.
The other side of the plan is to throw away as little as possible, to be self-sufficient in air and food. The Russians know more about survival in space than any other nation. It takes 2 tons of supplies to keep a cosmonaut in space for a year. But they know that for journeys to the planets, they'd have to do better than that. In Siberia, for years they worked in secret on space colonies as part of the failed Soviet moon program. At Krasnoyarsk, in the Biophysics Research Institute, they built BIOS 3. It could have been the prototype of a moon base. Experiments have now come to a halt. Scientists here are now searching for funds to continue and promoting their work as part of a much wider effort for human beings to break free of Earth.
Колыбелью для всех нас является Земля. Как можно выйти из нее? Необходимо создать для человека маленький мир, который мог бы выполнять для него те же функции, которые выполняет для нас, для всех здесь, большая биосфера Земли.
3 crew members spent 6 months sealed into BIOS 3. All their water was recycled. Their urine, the humidity from their sweat and breath were used by humans and plants alike.
Как две чаши весов. На одной чаше человек, который выделяет углекислоту при дыхании, выделяет жидкие твердые выделения, это проза жизни, но это жизнь, потребляет пищу, кислород и чистую воду, на которой существуют организмы, которые могут потреблять все, что человек выделяет, и поставлять ему то, что он требует.
Normally, it would take acres of open field to support a human being. In BIOS 3, the crew grew wheat, threshed it, and finally baked their own unleavened bread. The carbon in these grains had been eaten and breathed out several times. Now, they were to eat it again.
У нас, хлеб у нас был свой и очень вкусный. А раз хлеб свой, поэтому он действительно будет вкусный. Во-первых, это был самый питательный хлеб, калорийный, и съели мы его с удовольствием.
But if food was no problem, they had trouble with the air. The plants produced too much oxygen, and the crew had to build an incinerator to burn plant waste to get the level down. Keeping the balance of gases right in a small biosphere was the principal problem that the experimenters had to solve.
Это выглядит легко, так как легко выглядит все, что уже, все трудности, которые уже преодолены. В чем здесь трудность? Это просто, когда вокруг нас почти безбрежная, бесконечная большая биосфера Земли. Она стабильна за счет своей избыточности. Там много флюктуаций, но в среднем процесс получается стабильным. И то, что та стабильность, которую природа, если хотите, Господь Бог, создал для большой биосферы, мы ее теряем, уменьшая. И возникает проблема, как управлять маленькой системой, чтобы сохранить в ней стабильность. То оказывается, что можно иметь стабильный процесс, в котором, например, всего 30 квадратных метров могут кормить одного человека. Но мы вместе с тем, как всегда это бывает в исследовании, вместе с основным результатом «да» получили много вопросов.
That's been borne out by the experience of Biosphere 2 in Arizona. For the past 18 months, 11 people have lived in a miniature, monitored version of the world outside. Much larger than the Russian BIOS 3, it includes animals and fish, as well as plants. They too have had serious trouble with their atmosphere. They've recently had to add oxygen artificially to survive. In such complicated systems, it's hard to predict what will happen. That's why the Russians are turning to very simple systems to understand how biospheres work and how to keep them stable.
Здесь у нас есть два звена. Одно звено продуценты. Оно выделяет кислород, поглощает углекислый газ. Другое звено консументов. Оно поглощает кислород, выделяет углекислый газ. И таким образом, когда они соединены вместе через систему шлангов и прокачки воздуха, они помогают друг другу сосуществовать. Таким образом, вот в этой системе они завязаны. Это хлорелла, производитель кислорода, который подается в систему, и дрожжи его потребляет. Они выделяют углекислый газ, который потребляется хлореллой для роста клеток. Таким образом, мы имеем цикл по газу, один из основных циклов, который работает довольно быстро. Таким образом, вместо того, чтобы иметь дело со всей биосферой, мы имеем дело с очень простой моделью. Мы хорошо знаем, что дает каждый элемент этой системы. Мы можем их объединить, и они работают с очень большой скоростью. Мы можем построить хорошую математическую модель этого явления, и главное, сопоставить ее с тем, что имеет место в лаборатории. Вот. И на основе уже сопоставления модель, эксперимент, мы можем наконец понять, как работают биотические циклы.
The intention is to build up computer models of complicated ecosystems, to be able to predict how to get an equilibrium between plants and animals, both in enclosed bases and eventually over a whole planet. NASA scientists, for their part, are looking for examples of Earth plants which could start a cycle on Mars to support life under open skies. Chris McKay has been recording his search for life.
In the Gobi Desert, you find in these very lifeless plains rocks on the surface. You pick up a white rock, you find a little thin film layer of algae. And what's happening here is these rocks are fairly transparent. Light can get through the rock and reach the algae beneath, so there's enough light for photosynthesis. And the rock acts as a water trap, while the rest of the environment is too dry to support life. Now, we're not proposing that this exact rock be sent to Mars as the first organism on the planet, but it can teach us lessons in how to select, how to craft the first organism that does get sent to Mars. So, in some sense, life on Earth will provide the blueprint for life on Mars.
But Mars is far more hostile even than the Gobi. And to establish such organisms, the terraformers would first have to give the whole planet a much warmer, thicker atmosphere. To do that, Chris McKay, like Robert Zubrin, proposes using the principle of leverage.
Obviously, changing a planet is an enormous project. When you imagine changing Mars, if you imagine, say, just the size of the atmosphere, it's enormous, and you have to factor that thinking in. And what that drives you to is thinking in terms of ways in which a small change that you might introduce could be leveraged and which could and be amplified by natural processes. For example, there's an enormous amount of sunlight streaming on Mars, hitting the surface and just radiating back out. To warm up the planet, what you need to do is capture some small fraction of that sunlight and trap it in with a greenhouse effect. So what you'd look for is gases that are highly effective at trapping sunlight and holding that energy close to the planet.
Those gases do exist. CFCs, chlorofluorocarbons, are known for their ozone destruction, but they're also very powerful greenhouse gases, and in theory, they could be manufactured on Mars from local materials and released into the atmosphere to trap the sunlight.
If we imagine a time-lapse movie of what it would be like to warm up Mars, the first scene would be introducing these greenhouse gases. You'd be pumping them into the atmosphere. As you pump them into the atmosphere, the planet would warm a little bit. As it warmed a little bit, CO2 that's absorbed into the soil, like water is stuck onto a sponge, will start coming out. The CO2 is also a greenhouse gas, and that warms the planet even further. Eventually it gets warm enough that now the water starts melting. The permafrost melts, the water vapor starts getting into the atmosphere. Water is an additional greenhouse gas, making it even warmer still. And the feedback continues, and eventually you've triggered a hot, warm, moist atmosphere. At that point, you can in fact stop making these greenhouse gases because the thick CO2 in the water vapor will do the job for you. Once Mars has a warm, moist atmosphere, thick CO2 atmosphere, you then could start introducing algae and their cousins, the bacteria. One of the key problems on Mars is maintaining the carbon balance. On Earth and on Mars, presumably, once we activate its biosphere, there'll be a tendency for carbon to get locked up as limestone, carbonate. On Earth, tectonic activity, volcanic and tectonic activity, recycles that limestone back to CO2. On Mars, there is no plate tectonic, so there's no clear, not clear how you would achieve that recycling. But it may be that there's organisms that can do it for us. There's some preliminary reports that there are algae that are capable of breaking down carbonate and releasing the CO2. And you can imagine integrating them into a biological cycling system that completes itself and recycles that carbonate and bringing back the atmospheric CO2. So on Mars, biology would do what on Earth geology is doing.
Once the bacteria were established on a warmer surface, McKay plans to introduce plants into a cycle which would eventually support human life.
We have estimated that the amount of time it would take to warm up the planet, to get it to the point where it was habitable for plants, is about 100 years. The next step, taking that CO2 and turning it to oxygen is enormously harder. And that, we calculate, would require 100,000 years.
These ideas were published in an agenda-setting article in Nature, but even the authors of the paper disagree about whether their scheme would work.
I mean, people are altering the direction of the Earth all the time by making further changes, so you'd have to allow for that.
Dr. Owen Toon, one of the co-authors, works with Chris McKay at NASA, and he is cautiously optimistic.
In a lifetime, you have the opportunity to see what it's going to do and make a change, or do you have to wait generations to see what's happening?
The third author, Dr. James Casting, is much more skeptical.
Well, I was brought into the paper to add a touch of realism. You know, I have some doubts as to whether you can really do this easily on Mars. Some things are possible, some aren't.
Dr. Casting is an atmospheric physicist who specializes in computer modeling of climate, and his doubts are centered on the transformation of the Martian atmosphere.
To get a significant amount of warming out of the chlorofluorocarbons, you'd need to have levels that were probably 1,000 to 1,000,000 times higher than on Earth. And because of the fact that Mars doesn't have any oxygen, doesn't have any ozone, the CFCs are actually shorter lived on Mars than they would be in Earth's atmosphere. On Earth, they last about 100 to 300 years. On Mars, they would last only a fraction of that time. And so you would have to, we calculated in this paper, you'd have to produce these things at a rate of about 10 to the 6 times greater than we are producing them. That's 1,000,000 times greater than we're producing them on Earth today. That's totally unrealistic.
Obviously, over the many decades and centuries or whatever, chemists might come up with better gases that require less energy, easier to make, or maybe even gases that are made biologically, so they're made by microorganisms, making it all much easier. So we should differentiate between the particular design that we use to illustrate that the concept is possible, that it's science, that we're talking science, not science fiction, versus what might actually happen when people actually do this in 100, 150 years or whatever.
Now, Chris is an optimist, and he thinks that we can discover such a gas or such gases if we look for them. And I'm just not so convinced that that's the case. Maybe something like that exists, but maybe it's technologically impossible to do that.
Open the flood control valve. But, Your Majesty, you wanted them captured alive. Are you going to obey?
Chris McKay's plan also requires water on Mars, and plenty of it. The question is there enough there to do the job?
Water on Mars is one of the most controversial aspects of the planet's history. The reason for thinking that there's a lot of water on Mars is that we just see a lot of evidence of water erosion. Particularly when we look back at some of the older surfaces on Mars, surfaces that formed billions of years ago, we see lots of valleys that just look like terrestrial river valleys. They have tributaries, they branch and increase in size downstream. They just look like river valleys, except because they have no water in them. In addition to those branching valleys, there are other features that have been interpreted as large floods. This is a picture of Kasai Valles. You can see now in the middle of Kasai Valles a streamlined island. We see islands like this in very large flood features on Earth, and this is one of the first clues that suggested to us that this was truly a flood. You can see the scour marks here, these curvy linear scour marks. We see those on the bottom of large flood features on Earth also. So we have valleys, valley networks, we have these large channels. We also have additional evidence of water. Here you can see a type of crater that we call a splosh crater. It looks like you've just thrown a pebble into mud. And indeed, that's probably very close to what actually happened. You had a large meteorite come in, this ice or water-laden ground, and then the material which is ejected is full of water, and it lands on the ground. It just continues to run out, just as though it were mud. I just believe that there's a lot of evidence for water on Mars.
The latest radio wave measurements suggest the surface is even drier than had been thought, but the belief is the water is frozen hard in old water tables deep underground. The extra carbon dioxide, which Chris McKay needs to start his thicker atmosphere, would be held in a layer of loose dust and rock called the regolith. The dust is there. Dust storms have been observed even by telescope from Earth, and the surface of dust grains can hold gas like blotting paper holds ink. But would there be enough gas? At NASA's Ames lab, Aaron Zent is testing the ability of soil to hold CO2. He's using volcanic dust from Hawaii. From Viking data, it's thought that the fine Martian dust is similar. It's sealed into a test tube and cooled to Martian temperature. CO2 is then passed over it to measure how much it absorbs. The sums are complicated by the fact that the presence of water reduces the amount of carbon dioxide the regolith will hold.
One of the major uncertainties with Mars right now is how much CO2 is there on the surface. There's probably a fair amount of CO2 that's adsorbed onto the regolith, and if you were able to release that CO2, you might be able to produce a surface pressure that's on the order of 1% of Earth's atmospheric pressure. Now that's a lot of CO2, but that's not enough to warm Mars.
That's the sort of doubt that the Mars Observer mission might start to settle. It should start sending back results later this year. It will examine the surface at different visible and infrared wavelengths, detecting more accurately the types of rock and dust on the surface. Russian missions are scheduled to follow in 1994 and 96. They plan to send sensors down to the surface, like the Viking lander, to analyze it more closely. Considerably further off is a plan to return samples of material from the Martian surface to Earth. For geologists, it's then they will begin to get hard facts.
We really need those samples from the surface because these measurements that we've been made from orbit often tend to be ambiguous until you have ground truth, and we really need that ground truth.
Mars may be beautiful and fascinating, but scientific detail is hard to come by. And that means that terraforming enthusiasts often disagree. Martin Fogg is a graduate geologist. He's not a professional scientist, but he is a member of the British Interplanetary Society. He edited special terraforming editions of the Society's journal, which had published several of Chris McKay's early articles on the subject before it was mainstream enough for the usual professional journals. He believes that McKay's runaway greenhouse method will not go far or fast enough.
Their model for the production of this CO2 atmosphere, I think, is far too optimistic. It works too quick, and it produces far more CO2 than is likely to be there. And that doesn't take into account the production of your seas, your oceans. Mars will need to be wet as well as being warm. You have to somehow get the heat underground to the ice, where the ice can melt and start to drain into the low areas much faster than it would occur just by very slow conduction of heat from the surface. I see no alternative to the injection of very, very, very large amounts of heat deep underground artificially. It could be done, but it would be an immense undertaking.
The solution Martin Fogg proposes is based on something that's been done frequently on Earth: underground nuclear explosions.
You're going to have a very powerful, compact source of energy. And the only one that we know of now that really fits the bill would be thermonuclear energy.
5, 4, 3, 2, 1.
This is, of course, quite a scientifically embarrassing thing, because everybody thinks of this sort of thing for its military usage. But it's just energy, and I can see no alternative to speed things up.
Those kind of approaches tend to be rapid and uncontrolled and hard to predict and hard to steer. And they also, by their nature, tend to be dangerous to humans that might be on the planet. If Mars is being terraformed by Martians that are part of a scientific settlement there, or a long-standing settlement, they may not want to have their habitats endangered. The other problem I have with them is that these approaches don't seem to lend themselves to sort of a continuous cycling system. The way we have on Earth, our atmosphere is continuously recycled by biological processes. These natural geochemical cycles, in fact, in some sense, terraform the Earth constantly. Over and over and over again, the Earth is terraformed by these natural cycles. Only in the case where there's absolutely no way of finding a consistent biological solution would I go to an engineering, a brute force method, such as detonating weapons. And even so, we should be humble in that the amount of energy that we can harness, if you take the combined nuclear weapons of the entire world, the United States, all of Europe, the multiple countries of the former Soviet Union, put them all together, that energy release is only equivalent to about half an hour of Mars sunlight.
Chris McKay's preference for biological methods puts a premium on energy from the sun. On Earth, it drives the entire planet's biosphere. But the intensity of sunlight on Mars is only half that on Earth. Even if the planet could be transformed initially, left alone, it would slip back to its cold, barren state.
Finally discovered the source of the terrific power Ming controls. The power is derived from a strong beam of light, reflected from pure selenium, a new element which gives the light great properties and permits it to be transformed into other forms of energy.
Where does the light come from?
Where all light and power originate, the sun.
Capturing sunlight from space is no longer science fiction. Last week, the Russians made a first trial orbit of a small mirror to reflect sunlight back to Earth. They hope eventually to orbit much larger mirrors to lighten the Siberian twilight. But warming a whole planet would call for gargantuan engineering. The mirror would need to be about a third the area of Mars itself. Terraforming proponents in the British Interplanetary Society have done some calculations of the kind of mirror required.
Possibly the simplest arrangement for such a mirror is an annulus around Mars at a distance of perhaps 25,000 kilometers, and maybe a strip some 300 kilometers wide. The mirror as a whole is in orbit about Mars. The pressure of light from the sun blows the mirror away from Mars, but the planet's gravity pulls it back. These forces balance.
It wouldn't be a rigid structure. Very thin, it would float in orbit. Any movement would be countered by computer-controlled tabs. When they faced the sun, they would be gently pushed back by sunlight. When they faced away, the mirror could drift back. At this stage, this is all purely theoretical. Paul Birch proposes that Mars's moons should be mined for the materials to build the mirror itself. This would reduce the cost of getting them into orbit.
This is a very simple, crude structure, which, although large, should be quite easy to construct.
Mirrors, greenhouse gases, and biological engineering are the preferred methods of the terraformers. But others believe that their goal of a habitable planet with open skies is impossible, that the fundamental nature of Mars and the laws of physics are against them.
Although Mars has only just a little over the quarter of the Earth's surface area, you need something like 3/4 of the mass of the Earth's atmosphere to produce a one-atmosphere pressure that we're used to on the Earth on the surface of Mars. That's a lot of gas. It probably isn't there. So if we put a roof over it, and the roof could be anything from 1 to 3 kilometers above the surface, we need only a very small percentage, maybe between 5 and 10% of the amount of gas we would need for a normally fully terraformed Mars, and that's attainable.
Engineer Richard Taylor proposes sealing the atmosphere under a roof retained by huge buildings, up to 2 miles high. The volume would be vast enough to contain a stable biosphere. He calls the idea para-terraforming.
The low gravity of Mars is a bad thing for orthodox terraforming, but it's a good thing for paraterraforming because the logistics of getting things up and down into orbit and actually building very large structures on Mars are much easier because you've only got 2/5 the gravity. We initially build of our world house just a single cell from which you can extend your construction steadily over the planet's surface. So it's rather like dropping a plant seed, and it grows and it spreads. And the great difference between this and terraforming is the fact that you can live on your paraterraformed worlds from day one. But with terraforming, you have to spend all the money, all the time, all the manpower, and wait maybe hundreds or thousands of years before anybody can live there.
Main bombers, the raid has begun.
But the problem with a huge greenhouse is its vulnerability.
Emperor's ships. They're dropping gas bombs.
Get out on the roof. Maybe we can
Vulnerability not so much to bombs as to meteorites. All the Martians' eggs would be in one eggshell. But Chris McKay's opposition runs deeper.
If you're going to build a roof over the world, you probably should do it on the moon. It's a lot closer, it's a lot smaller, it's probably a lot easier. What's unique about Mars in the solar system is that it's the world in which we might do a natural biological planet.
You can either adopt Chris's attitude, which is, well, if we can't have the ideal solution, I don't want anything. But I would argue in life, in the world we actually live in, you never have ideal solutions. And the point is, if you want to live there, then you may have to adopt a solution that is less than ideal.
Putting a roof over Mars would in some sense miss the whole point of why you're going to Mars in the first place. Just the notion of planting a seed, going to a barren planet, a lifeless planet, and bringing life there. And I don't just mean human life, I mean life, the whole ensemble of organisms, and trees and microorganisms, birds and what have you, and introducing them onto another planet and having them go forth and multiply, if you will. It's, to me, that's a creative act, and it's part of what I think it means to be human.
McKay's Martian dream would take centuries to realize, but plans for human colonization are being laid here, in one of the most crowded cities on Earth. A major Japanese construction company has for 3 years had engineers designing a Martian settlement. And they have produced a computer-generated video of their project. The Obayashi company engineers have imagined the journey of a small boy to see his father at the Mars base. The project was started to promote the company's high-tech image in the construction business, but it used the best current scientific ideas about how such a journey would take place. They envisage the colonists living off the Martian land, drawing energy from the Martian winds. Their atmosphere would come from a huge version of Bios 3. Plants, insects, and humans would form a biological cycle and a space in which the colonists could relax. It would be the start of permanent occupation. From bases like this, they could begin the terraforming of what would now be their planet. A leader of the design team, Dr. Yoji Ishikawa, had spent a year working with Chris McKay at NASA before he came to work on the Mars City project.
Okay, this is our design of the Mars base in the middle of next century. The 150 people is supposed to live here. At the north end, we have the control center here, and also the safe haven. If something happens, people can hide under the mountain. Then, along the center line, we have the habitats, and also the inflatable structure. The next line is a greenhouse to supply food and oxygen.
It's rare for a commercial construction company to be putting money into research like this. But Obayashi felt they needed a foothold in what they saw as the business of the future.
So far, the space business means making rockets and artificial satellite. Only the National Space Agency and the aerospace company did that. next century, we have to build habitats on Mars. So that means that the construction company has lots of chance on the space business.
And following Zubrin's principle, they plan to use local materials. In their laboratory, soil engineers have added small quantities of water to bentonite, a clay believed to be similar to Martian soil. They found that by compressing the mixture, they can make a good foundation cement from something like Martian materials. As befits a commercial company, the engineering is practical. The ideal is to have a functioning Japanese colony within a generation.
This is in the middle of next century, and 150 people live here. There's a male and there's females. So I expect the first baby will be born on Mars in 2057.
That would be the 100th anniversary of Sputnik orbiting Earth. It's a romantic notion. So how real are all these projects? Although engineers and scientists are thinking hard about colonizing and terraforming Mars, it would be hugely expensive. There's no possibility that any such project would be financed soon, if ever. It's still Martian dreaming. But terraformers claim that they're not drawing up a blueprint, rather establishing the scientific credibility of an idea.
Human civilization already has the capabilities to change Mars, to terraform Mars. That doesn't mean that when we decide to do it, that'll be the way it'll be done. In fact, technology will advance, it'll be faster, it'll be better. If anything, it'll have to be faster and better than what we propose. But we are demonstrating that it's possible, trying to move the topic away from science fiction and into science.
But maybe it's still an engineer's version of the old fascination with adventure on Mars.
People have always been fascinated by gigantic engineering feats, but all of them pale in comparison to the notion of terraforming Mars. We're beginning to understand more and more that enormous engineering acts on the surface of the Earth have repercussions that we don't quite understand ahead of time, and it can be dangerous. Whereas in this thought experiment of terraforming Mars, you can justify doing this fantastically huge engineering feat without having to file an environmental impact statement. And you have this entire world that could become the new frontier. Mars as the continuation of the Wild West.
It's the only planet out there where one can reasonably expect that humans could go and establish themselves permanently for whatever reason. People could go and live on Mars. They can't go and live on Jupiter, but they can go and live on Mars. And I think just because it's available, almost we have the capacity to go there already, that it's inevitable that we will go.
If you'd like a transcript of this programme, please send a cheque for £2 made payable to BSS 2, Horizon Mars Alive, PO Box 7, London W3 6X.